Okay, so if you recall, of course, the gradient descent algorithm requires us to compute the gradient of the function being optimized, right? So in this implementation, I use this function, my gradient underscore central difference. It's not an inbuilt MATLAB function. It's just something that I wrote at some point that computes approximately the gradient of the objective function at the current value of the parameters. And well, f accuracy, I'll say what that is actually. And that gives you the gradient of f. Okay. So how is the gradient computed? Okay, so we can compute gradients a variety of different ways. If you have a simple enough function, let's say f equals y sine x, just to take a random example, where it's a function of two variables, or your parameter set p, p1 and p2 are basically x and y. Okay, so one way to differentiate or find the gradient is to just do it analytically, symbolic differentiation or analytical differentiation. We can get these partial derivatives pretty straightforward. This works for simple functions. It may not be very efficient for functions that involve very complex simulations or calculations to be evaluated. It's pretty accurate, right? Because it's analytical, it's pretty accurate. Specifically, to the extent that we can evaluate f accurately, let's say to 15 decimal places, generally we will be able to approximate these derivatives to around that level of accuracy, if not 15, 14, like close to 15 significant digits. But the more complicated the function is, less accurate the evaluation will be. Okay, generally. In any case, so let's see how that works in MATLAB. So if you have some variable, let me just demonstrate symbolic differentiation in MATLAB. Many of you may know this already, but if you have some function, let's say literally that function f equals y times sine x. Now if you do that, MATLAB is just going to say unrecognized function or variable y and not like it. But you can define variables to be symbolic variables like so. Okay, MATLAB is taking a little bit of time, presumably because I'm recording this video. Strange. It's an unusually long amount of time. Okay, so it's done it. So what we've done here is we've declared the variables x and y as being symbolic. So if you don't declare it as symbolic, MATLAB will assume that x and y are numbers, double precision numbers generally by default. And because we've not defined it, it complains about it. But once you declare x and y to be symbolic, then MATLAB is happy to allow expressions of this form, because, well, they're just symbols now. Okay. Now we can differentiate f with respect to x, and it gives you this answer, which is the right answer. Now this essentially computes the partial derivative of f with respect to x. Okay, and you can check that that's the correct answer, and then we can do that with respect to y. Okay, sine x, that's right. Or we can say gradient. There is another function in MATLAB called Jacobian, which basically is the gradient in this context. We can say Jacobian of f with respect to x comma y is basically this vector, which is the gradient, right? And that's it. Jacobian just gives you the matrix of partial derivatives. It's a bit more general than gradient because it also applies even if f is a vector as opposed to a scalar. Right? In this case, f is a scalar output, but if there are multiple elements in f, then it will just give the gradient of each element of f as a separate column. Okay, so yeah. So if f was something like that, and then we went Jacobian of f x comma y, then it gives us well, I guess in this case the gradient is actually each row. The gradient of the first element of f with respect to x and y is the first row, and the second element is the second row. Okay, so Jacobian is a bit more general, but basically it gives you the gradient. Okay, so that's how you evaluate the gradient of the Jacobian. So we can go back to what f is. And then if you wanted to evaluate the value of the gradient at some point, we can do the following thing. We can say substitute g x comma y, say at some point 3 comma 4, and we will get a numerical value. Now the numerical value is expressed in this sort of analytical looking way. Instead of writing just a floating point number, it's written in this manner. So if you want to convert it, convert the thing into regular double precision numbers, you can convert it like this. Okay, things are really slow, I think mainly because my computer is running a bit slow, but things should be much faster hopefully on your computer. Okay, so those are the numbers. So it just evaluates 4 times cosine 3, and that's this quantity, and sine 3 apparently is this quantity. Okay. Okay, so that's how you do that. By the way, I didn't quite talk about this much more, but symbolic, if you're not familiar with the symbolic toolbox, it's incredibly useful for a variety of things. Let's say we say f equals 1 plus 3 plus 4, 3 plus x power 10, I don't know. And let's say for some reason you wanted an expansion of this f with respect to x, so or just an expansion of that quantity, you can just go expand of f. So that's the expansion. We already saw how to differentiate things. We can integrate, say with respect to x. Okay, so it does that correctly. I think we can do integration with limits, like x going from say 1 to 3 something. Okay, so now it plugs in those limits, does the right thing, so that's a definite integral. Previously it was an indefinite integral. Okay, so symbolic can be very useful. So that's one way of doing derivatives. Okay, in the next little video we'll talk about the next method, and then we'll talk about a third method for computing derivatives.